Okay, so before we move on with the rest of chapter 22, I wanted to show you a little demo with this radio that I have here. So I have the radio here on, and it's playing, oops, it's going to be playing an AM signal, and I apologize, AM stations are never very good. So when I had this playing earlier, it was, uh-oh, it was some crazy guy talking about conspiracy theories. So we'll just have to listen. We'll just have to grin and bear it. But I wanted to show you a demo of this example that's up on the board, which is that an AM, right? This part here on my radio is actually an FM signal receiver. So, and you can kind of point this around, and the reason that we're pointing it around is to point at the antenna so that we get a better way to capture the electric field that's oscillating up and down on our antenna. AM radio waves are actually really long. They can be like 75, 100, 200 meters long. So they're really long. We're never going to be able to design an antenna that's going to fit on something like this that's long enough to be resonant with an AM radio wave. So instead, we use a coil. So inside of this is a little coil, and that coil is not going to be designed to capture the electric fields, but it's going to capture the magnetic field. So it's going to be resonant with the magnetic field that's going in and out of the page here like this. And so when I turn this on, I seem to not understand how this thing works, but I think I got it now. So what I'm going to do is rotate this 90 degrees.
Hello. I like Blackula. But Blackula. Yes. But you're mellow. You're like the friendly Blackula. You're actually more like the chocolate. What was Blackula's gimmick? I've never seen this movie. There's black plate.
So what you heard with that is as I rotated this, right, there was one configuration where we caught the magnetic fields best. A more physicsy way to say that would be to say that we oriented the loop such that the magnetic flux through my coil was maximized. And then if I rotated it 90 degrees, then now there was no flux through the loop, and there was no induction that happened inside this coil antenna. And because there was no induction inside the coil antenna, there was no current inside the coil antenna to send a signal to be amplified with the microphone. Okay. So the next example to go through here is this one. And so we want to double the intensity of an electromagnetic wave, and what do you need to do to the electric field? So let me grab my equation sheet. That's not my equation sheet. Here is my equation sheet. So let's find the equations that we're looking at. So, right, we have here the chapter 22 equations on our equation sheet with some constants up at the top. So remember, we already talked about what C is. And these equations here are the equations that talk about the intensity of the magnetic field. Okay, so this is I is intensity. So let's copy down. Actually, we did this in the previous video, so I'm not going to rewrite them, but that's where they are. And if we want to double the intensity of a magnetic wave, you need to do what to the electric field? So I'm going to come over here, and I see this right here is an equation that has only electric field in it. So I will say that, what is this? Quick check. Intensity is epsilon naught times the speed of light times e squared. Epsilon naught is just a number you look up on a table. It's this number right here. So these two don't change. And if I want to double something on this side, then I will say that what is it that I need to do to this? So if I double the electric field, then I'm actually quadrupling what's going on the right-hand side here, right? So that's, if I double the electric field, then I would have a 4 over here. So what I really want to have is E naught times C times something times E squared. So like, what is the number that we were going to throw in here to multiply the E? And we want something squared equals 2. I guess maybe that's the best way to say it. What number squared equals 2? And that number is the square root of 2. So I will say that epsilon naught C times the square root of 2 times E squared is 2I. So we double the intensity by multiplying the electric field by this factor of the square root of 2. So if we come to the square root of 2 is 1.414. So the answer to this is C. Okay, so there is that. Okay, so here's a thought question for you. So we've been stepping through electromagnetic fields, right? So in chapter 16, we talked about how the electric force depends on the electric field. So you need both an electric field and a charge to feel an electric force. In chapter 20, we talked about how a magnetic force depends on the magnitude of the charge, the speed of the charge, and the magnitude of the magnetic field. So we need a magnetic field and a moving charge to feel a magnetic force. So are these fields, this electric and magnetic field, are they real things, right? If you think back to the electric field, where we were trying to visualize what the shape of a sheet would look like if it exists, because we think about the charges altering the space around you. We obviously can't see this, it's invisible. So are they real things, or are they just mathematical constructs that evil physics professors have created to help us solve problems? And the answer to this is that they are real. And the reason that they are real is because they carry energy. Okay, so we can think about electromagnetic waves as being coming from the sun. So the way that we get energy from the sun is that energy travels via an electromagnetic wave. So via these electric and magnetic fields, they travel through a vacuum and warm our planet and give us a nice toasty thing. Okay, so the reason that these fields have to be real is because they carry energy. Okay, so that is all I wanted to say about the chapter 22. I will say that there's one other video that's posted that talks about how microwaves work to heat your food, which is something that I also talked about in a previous video, but there's a very cool demo in that video, so I'd really recommend that you watch it. The last thing that I want to talk about is the photon model of electromagnetic waves. And so we have a few different ways of thinking about electromagnetic waves. And actually, we haven't fully talked about this, but actually electromagnetic waves are light. So that is, those two words to me mean the same thing. So light comes from the sun in the form of an electromagnetic wave. Okay, so light is a wave, and it behaves in the way that all waves behave. And we're not actually going to end up having enough time this semester to talk in too much detail about that. But there's a lot of interesting properties of waves, light, that make it clear to us that light behaves like a wave. Light also is this crazy thing, because if light was just a wave, if you reduced its intensity, then it should just grow dimmer, but you'd see the entire image. And anybody who's ever seen a grainy photograph, so let me get me out of the way here. Here's a grainy photograph. Has seen this, the pixelated images. So back in the day when we used to use film to make photographs, right? in a dim light, what you just see is this really pixelated image. And this little pixelated image is not at all what you'd think about something that comes from a wave. Instead, it seems like light is arriving in these tiny little discrete packets of energy. And it turns out that light does arrive in tiny little discrete packets of energy. And we call these discrete packets of energy photons. So a Geiger counter is something that can detect gamma rays, and I'm trying very hard to get this because I did not get it up on the screen before. You have to bear with me for a minute. As another example of light behaving like a photon, like a wave, like a particle in the like a photon.
So here we are at Tigalen near Bubry.
This guy has taken a Geiger counter. So a Geiger counter is a way that we can detect the presence of radiation, but radiation is electromagnetic waves, and so he's taken this Geiger counter here, and I want you, basically, the reason I'm playing this is so that you can hear the Geiger counter going off.
Here is a contaminated area, so we're going to check
these little things. So he's taken this to the site of an old uranium mine, and uranium is a radioactive material, and so he's hoping to detect some counts of the Geiger counter.
Geiger-Müller counter here. It's not a very spectacular sight, and the counter is not picking up any radiation either, a little bit. So the mine is over there, and here we have some kind of evacuation canal, and apparently some wastewater has gone through, as you can see. It's quite active at the moment. And on the computer.
So what I wanted you to hear was the beeping of the Geiger counter, right? So it's making these little ting 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 type noises, and that is physically the sound of photons of high energy electromagnetic waves, high energy radiation hitting this Geiger counter. So as he moves it around, there's various places where it makes more.
We are at 1.9, almost 1.2 microsievert, which is about 4 times as much as background radiation.
Okay, and so you don't actually need to go to a contaminated site to actually see this, right? If I had a Geiger counter here and I turned it on, it would start beeping because there is high energy radiation all over. It comes from all sorts of just rocks that are in the earth, bricks that are made out of this house, that make up this house, and all sorts of things like that. Okay, so let's get together some properties of a photon model of light. Okay, so our photon model of an electromagnetic waves has 3 basic postulates. The first one is that these waves consist of discrete massless units that we call photons. So it travels in a vacuum at the speed of light. You can imagine these like massless, invisible particles traveling through a vacuum at the speed of light and carrying energy with them as they go. The second part about this is that each photon has an energy, and that energy depends only on its frequency. So high frequency waves, the ones that go up and down very quickly, have more energy in an individual photon. This letter here, H, is Planck's constant, and that is a number that you look up in a table. It's on your equation sheet. Right? That is not something that varies. So the energy in individual photons depends only on the frequency. So electromagnetic waves come in little discrete chunks or packets of energy, and each little chunk has the energy h times f. And the third part of our photon model is that when you add together a sufficient number of photons, then we start to see wave-like behavior. So it's when we have billions and billions of photons, we're kind of lose the particle nature of electromagnetic waves, and it starts to behave more like a wave. But when there's just a few of them, say a few or hundreds of them or fewer, that's when we start to notice these more particle-like properties of waves. So let's find the energy of a photon of visible light. Okay. So we say that 550 nanometers is the average wavelength of visible light. And let's figure out what the energy of a photon with this wavelength is. And also let's figure out how many visible lights are emitted for every second. So part A, we will just say that the energy of a photon is h times f, okay? So we need to figure out the frequency of this wave. So we will use the fact that c is lambda f to solve for the frequency, because we haven't been told the frequency, right? Nanometers is a unit of length, so that must be its wavelength. So we'll use this equation to calculate the frequency, and then we'll plug the frequency in to find the energy per photon. My pencil is out of lead. Okay, so the frequency is c over lambda. So the speed of light, we'll look up in the table and see that the speed of light is 3 times 10 to the 8th meters per second. And we've been told that the wavelength is 550 nanometers. So I'll write nano is 10 to the negative 9. So I'll write this as 550 to the negative 9th meters. And we'll have to calculate that. So 3 times 10 to the 8th divided by 550 times 10 to the negative 9th. And that is a very large number, 5.4545 times 10 to the 14th. Our units here are the units in verse seconds or hertz. Okay, so now we're ready to plug that in. And we'll use Planck's constant, which is 6.63 to the negative 34. And let's just skip ahead here and see that this is 3.6 times 10 to the negative 19 joules. Save myself a little bit of work. So the units of Planck's constant are joules times seconds. That's the way that it's written on the equation sheet. So the units here work out. Joules times seconds divided by seconds is a unit of energy, which is what we were expecting. Okay, now let's do the harder part of this problem, which is part B. So we have 40 watt incandescent light emits 1 joule of visible light every second. This is actually why we don't use incandescent lights anymore. Incandescent lights are those light bulbs that we used to use that if you plugged them in, they got incredibly hot and you'd burn yourself if you touched them. We really don't use them anymore. They've fallen out of favor, mostly because they're really energy inefficient, right? And this is an example of that energy inefficiency, right? It takes 40 watts of electricity out of the wall, but actually only 1 or 2% of that energy goes into lighting up your room. The rest goes into heating up your room, which is pretty wasteful. So we don't use them anymore. So we have a 40 watt incandescent light emits about 1 joule of visible light energy every second. And we're going to try to estimate how many photons are emitted in the visible, how many visible light photons are emitted every second. So we will say that there is 1 joule, which is a joule, 1 joule every 1 second of visible. Okay. All right, so we have 1 joule every second of visible photons, and we know that each individual photon, let me just even adjust this unit, has a unit of, that has a very tiny little increment of energy per photon. I'm going to actually set this up as a conversion factor type question. So I want these units of number of photons. Okay, so I'm trying to sort of, we know this is how much energy is in 1 photon. Okay, and we want to figure out how much energy, how many energy of photons there is in every second. So we sort of have all the units here, but it's not quite clear how to do this. So if I start off with in 1 second, I will say that 1 joule has how many photons. So we're going to set this up as a conversion factor question where I want the units of joules on the bottom and the units of photons on the top. And that is where I have this right here, okay? So every 1 photon has this much joules. So every 1 photon has 3.6 times 10 to the negative 19 joules. And now I can think about multiplying these numbers together because I have joules on the top and joules on the bottom. And I will be left with the unit of photons in a single second, which is what I want. So let's turn that on and say 3.6 10 to the negative 19th is that. And let's just take 1 over it. And there we go with 2.8 times 10 to the 18th. And let's just round that to 1 significant digit because this problem is in 1 significant digit, which is about 3 times 10 to the 18th photons every second. Right? So the take-home point for this is that, right, this number here is huge. Okay, so individual photons have this tiny little chunk of energy. Okay, and the take-home message from this is like, how could we possibly, in normal life, we don't detect the photon nature of light, it's particle-like nature, because there's 3 to the 18th of them striking our eyes every second. Okay, so we'll say that no wonder we see the river, which is the waves, instead of these individual particles. Okay. Okay, so we say a single photon has an energy of 2.3 electron volts. Let me go and show you what I mean by that. If you look here at the equation sheet, somewhere we have talked about electron volts as a tiny little unit of energy. We haven't talked about it for a while, so I'm not, oh, there it is. On the very front of the very first page, we have that a unit of energy is an electron volt conversion to joule. So if I wanted to convert this to electron volts, I could say that 3.6 times 10 to the negative 19 joules. And I know that 1 electron volt is 1.6 to the negative 19th joules. And we could kind of do these two numbers divided by each other, and you see that they both have this times 10 to the negative 19th factor in them. So it's just as simple as doing 3.6 divided by 1.6, and that's 2.3 electron volts. Okay. So individual particles, if you can think about individual photons having certain energy, and here's how much energy is required to do certain things. So to break a hydrogen bond between two water molecules. So this is that that water molecules have that strong dipole. So they have these sort of attraction through them. This isn't a chemical bond, but they're sort of stuck together because they have this strong dipole. We need 0.24 electron volts to do that. So a photon of visible light will break a hydrogen bond. It will also deal with metabolizing one molecule of ATP. It will not break the bond between atoms in a water molecule. So no matter how intense the visible light is that is hitting something, it cannot break apart chemical bonds, okay? And this is meaningful because this is where we start to get into this idea like there's some kinds of radiation that are harmful to us, right? UV, gamma radiation, X-rays, these types of energies that we're sort of aware in some way are harmful to us, right? That is because individual photons of those types of electromagnetic waves have enough energy to kind of do harmful things. So let's do one more quick check. So a typical analog cell phone has a frequency of 850 megahertz. A digital phone has a frequency of 1950 megahertz, and we want to compare the signal from the analog phone and the digital phone. So we'll move down here. This is quick check 22.4. And we'll look at these two equations here that have not the first time I've written both of them here. So that the energy per photon depends only on the frequency. So more frequency, more energy in a single photon, and also the speed of light is the wavelength times the frequency. Okay, so let me write this here. Right, so as F goes up, energy per photon goes up. So higher frequency, more energy per photon. Okay, and then so we'll come down here and now we'll say, well, what happens if we have a higher frequency? Remember, the speed of light is constant, so the speed of light will stay the same. And that must mean that as the frequency goes up, the wavelength goes down. So if we go through here, we have found that the shorter wavelength, so the smaller wavelength, has a higher frequency. So we will say that this analog signal has is the answer to that question. So visible radiation or visible electromagnetic waves are only one part of what we call the electromagnetic spectrum. They happen to be the tiny part of the electromagnetic spectrum that our eyes are sensitive to. They also happen to be the part of the electromagnetic spectrum that most of the energy that comes from the sun is visible as well. And that's probably why our eyes are sensitive to it, right? The energy that comes from the sun is visible light. It makes sense that we're evolved to have our eyes be sensitive to this little spectrum here. But infrared rays are are the way are electromagnetic waves, microwaves, things that work in your microwave weapon, FM and AM and TV waves. These are all low energy photons. And so as we move into these low energy photons, we can think about these as being the ones that just have, 10 to the 20 photons striking you every second. So we don't see the particle-like behavior of these types of waves very often. As you move into X-rays, gamma rays, and UV, now we're moving into photon energies that are actually pretty significant. And so it doesn't take as many photons to deliver a lot of energy. And that's when we start noticing the particle or the photon-like behavior with these higher energy radiations. So X-rays and gamma rays and some ultraviolet rays are what we call ionizing radiation. Okay, so these individual photons have enough energy to split apart molecules. And when that type of radiation strikes tissue, it can produce cellular damage, and we're all aware that exposure to that type of radiation over long periods of time gives us cancer and all sorts of things that we'd rather not deal with. I am going to actually stop here because this is a good place to stop, and we will pick this up with the next